Hi, I'm Jeff de la Bojardière, and I welcome everybody to the February CISL seminar. Our speakers today are 4 people from the CISL High Performance Computing Division and the NCAR Wyoming Supercomputing Center. Irfan Elahi, who is the NWSC3 Project Director, along with Bill Anderson, Michael Kercher, and Brian Vanderwende, who are the technical leads of the System, Facility, and Applications teams. Together, they will be providing an NWSC3 High Performance Computing, Storage, and Facility update. Please use Slido at the bottom of your screen to submit and upvote questions, which will be answered at the end. Thank you very much, and Irfan, take it away.
Good afternoon, everyone. My name is Irfan Elahi, and as Jeff mentioned, I'm the project director for the NWSC3 project. What we wanted to share with you is not only just the procurement process, which I think you will find interesting, but also what our plans are for the commissioning and deployment of the NWSC high performance computing, as well as the high performance storage resources. When we kicked off this project, the first thing we looked at was what is our strategic objective? Why are we getting this new supercomputer and storage resources? We looked at 4 main things that we focused on, which was we wanted to make sure that the new system is highly productive and it focuses not just on performance and time to solution, but also invests in new and emerging exascale concepts like GPU and accelerators, and also provide our users with the necessary infrastructure to burst out to commercial cloud. Now, we also wanted to make sure that we enable the environment for our users so they could optimize and refactor their applications and remain productive throughout the transition process. We do plan to keep Cheyenne for 6 months after NWSC3 has been commissioned, and we wanted to make sure that users remain productive during the transition. Now, once we had the strategic objectives, we wanted to translate those into specific deliverable scope. So after coming up with a lot of user survey and engagement with the user community, we decided that the NWSC3 system should be mindful of the user requirement, but not just the user requirement from our existing workflow, but also look at more where the future of HPC is going, more data-centric, more containerization, more use of accelerator and GPUs. But we also wanted to be mindful of the power and carbon footprint of the new system. So, when we started looking at NWSC 3 high performance computing and storage technical requirements, we made sure that these features and functions were part of the RFI and RFP process. Now, after engagement with the user community, SRAP, and our technology development division, we decided that the split of the compute portion should be in 80-20 with respect to performance capability, which we call CSAP. CSAP is basically Cheyenne sustained equivalent performance. And what that means is we took a number of CPU-only benchmarks and GPU benchmarks, and we ran them on full dedicated Cheyenne. And whatever we got performance was a baseline of 1. And so from there, we basically looking at our budget and looking at budgetary quotes and engagement with technology provider and analysis of the marketplace, we felt it would be safe to get at least 3 times more performance and capability on the new system than Cheyenne. And that's why one of our main requirements of the RFP was 3 CSAP. Now, I mentioned before that we wanted to make sure that we have adequate GPU and accelerator partition. So we decided that 80% of the CSAP would be CPU only and 20% of it would be GPU or accelerator. We also found that with our budget, we would be able to get 60 petabyte of usable file system space. And as I mentioned before, cloud bursting infrastructure was part of our requirement. And we also have significant investment in storage, in data analysis and visualization and machine learning cluster, which is called Casper, as well as our high-speed network. So we wanted to make sure that the new resources, both compute and storage, would integrate into our existing HPC infrastructure, which means that if you are sitting on Casper, you should be able to talk to or submit jobs on the new system, and you can see the same data and file system across both. And in order to do that, we needed to make sure that the new system would integrate into our network and we can kind of mount file systems across each other. Another thing we wanted to make sure that this system doesn't lock us out, it's extensible. Now, I do understand and agree that you are tied to a vendor, but you do have the option of different technology. So the system is architected in such a way that if you wanted to add a next generation GPU, we could augment that using the same racks, the same compute blades, and the same networking parts that are part of these resources. And we also wanted to see if we could extend the life of this machine beyond 5 years. So we have 2 additional years of options which we can exercise if we wanted to keep the machine for more than 5 years. Now, as I mentioned before, when we kicked off this project in 2018, the support, commitment, and cooperation of the stakeholder was very important for us, especially because this project was very complex and in magnitude, not just in complexity, but it was something pretty big. So we wanted to make sure that we have the right engagement and right focus. The project management team, the technical evaluation team, the business team, the benchmark facility team, along with the science requirement advisory panel. And I emphasize the SRAP because they were very pivotal and very instrumental in a lot of the requirements that we formulated for this RFP. Now, when we were constructing the SRAP panel, which consisted of diverse scientists from NCAR as well as member universities, we made significant effort to make sure that we have diversity, not just of subject matter expertise, but also diversity of gender and a good balance between NCAR as well as the university representation. And you know, we didn't just stop at SRAP. We also engaged the user community through a lot of user surveys. And we looked at, you know, the science areas, application code, third-party application, usage algorithm, job size, memory usage, threading use, IO pattern, and user workflow to see, you know, what lessons should we learn from the existing workflow and workload analysis on Cheyenne. So we architect the next system that basically provides our user the best value. We also were mindful that NSF is a stakeholder, so we engaged NSF very early, right after the kickoff. And we've been meeting with NSF on a monthly basis and sending them monthly reports throughout this process, and we'll continue to do that. We also engage other HPC sites like Oak Ridge, NERSC, and others. And we also engage the vendors and technology providers early. Finally, we also had a red team that reviewed the draft technical specification and provided valuable input and feedback, which we incorporated into the RFP. Now, I just wanted to share this, that this was a collaborative effort. We just didn't architect and design the system on our own. We had an RFI, 4 vendors responded to that RFI, and then we had a full day workshop with each of those vendors. And during that workshop, we collaborated, we shared a lot of information about our workflow, and then we basically changed some of the configuration in the RFI that was submitted by the vendors. And that helped with the specification of the RFP, because when we asked them to resubmit the RFI technical strawman proposal, it changed because we were able to give them insight on our memory requirement as well as our network requirement. Now, very quickly touching on this slide, that, you know, we did have challenges, not only because the US HPC market is changing. As you know, HPE acquired SGI, then they acquired Cray. So we don't have that many vendors left, and this is a concern. IBM was not price competitive. They could not meet the CSEP requirement. So that was a challenge. And then there are vendors like Dell who only provide codes for ready to ship product. Benchmarks that we have are complicated. Small vendors don't have the resources to basically take that benchmark and provide projection on their solution or what they're quoting. And definitely COVID played a part. And then also we have this Buy America Act, which means European vendors like Bull or Atos or even Chinese like Lenovo are not eligible. So what did the proposal come back and what was the decision that we made? So the solution for NWSC 3 is going to be an HPE Cray. As you can see, the system will be just about 20 petaflops in peak, 60 petabyte usable file system space. So this is more CSEP than what we had asked for. There's about 3.51 CSEP and 2.84 is CPU only. The rest 20% is GPU. Now, this is a Cray solution because HPE also has a system and we have a lot of confidence in the Cray team. So that's a good thing. Another thing is that we will have an on-site person from Cray that will be stationed at NWSC in Cheyenne. So response to problem and trouble would be much less because we'll have a person on site. And another thing is that this will have PBS. So it's the same scheduler that users have on Cheyenne. So this gives you a very high level view of how all of this will come together. You'll see on the left side of your screen, you see the box where we have the two types of cabinets, and I'll talk about both the Olympus cabinets and the River cabinets in more detail later on. But on the other side, you see how the network will be all connected. As I mentioned before, we need to make sure it integrates with our existing HPC infrastructure. So the vendor is going to provide us with Arista switches. These are all connected in MLAG, which basically provides failover. Good thing about MLAG is it's not just failover, it also basically provides you, in addition to redundancy, it multiplexes and provides more increased bandwidth. So that's a good thing. And you can see that we will provide you access to all of Glade and campaign storage, as well as Casper. So the Arista switches will be connected to our NCAR's own HPC and IO backbone, which is called Bifrost. So through that, we will be able to mount file systems that you see currently on Cheyenne on the new system. And then you'll be able to mount the scratch from the new system onto Casper as well. So a little bit detail about the type of nodes. As I mentioned, we have two types of nodes, CPU only nodes. So the CPU only node, you can have 4 nodes per compute blade, and there are 64 compute blades per rack or per Olympus cabinet. So that means you can have 256 nodes in one cabinet. And if you look, you basically have a single slingshot network injection, which means there's one network connection to one of the sockets. And then both of them have DDR4 8-channel fully populated ranks for optimum performance. So, and then this gives you basically a diagram of all the components in the GPU node. The GPU node is slightly more dense because it has GPUs in it, so you can only have 2 nodes per compute blade. As I mentioned before, same thing goes for GPU. You'll have 64 blades per cabinet and only 128 nodes per cabinet. In the previous slide, I mentioned we have 82 GPU nodes, which means you will have 4 GPUs per node, and each of these nodes will have 4 slingshot injections. So that then will give you about 800 gigabits per second out of this node. Now, in addition to the compute blade, you also have something called a switch blade, and that is for the slingshot. I've been using that term, and I'll describe that later on. Slingshot is the interconnect for this cluster. And this is a picture of the compute blade along with the switch blade. There are 8 compute blades and 8 compute chassis and 8 switch blade chassis. And when they are fully populated, you will have 64 compute blades and 64 switch blades. The compute blades are all loaded from the front, while the switch blades are from the back of the Olympus cabinet. So this gives you a picture of what the Olympus cabinet looks like. So the Olympus cabinet consists of one or more rows of these liquid cooled cabinets. And there are also 4 of these racks or cabinets will be connected to one CDU, which is a cooling distribution unit that serves the coolant and water to keep these compute nodes and infrastructure cool. The Olympus cabinets have 4 shelves. Now, each of these shelves will have 2 compute blade chassis and 2 switch blade chassis. And as I mentioned before, each of these chassis can have 8 nodes or 8 switch blades. Also, each of these rows also have a rectifier chassis and a power distribution unit. So this is what the topology of the Slingshot network or interconnect will look like. It's basically a 3-hop Dragonfly topology with 200 gigabit per link bandwidth. A full all-to-all network is provided within each cabinet. So each cabinet will have an all-to-all connection. But then each cabinet is connected in a global optical network using an optical cable to other cabinets. And as you can see by the red lines, the maximum hop between 2 endpoints from one node to another, there is 3. So it doesn't matter if you're going from first cabinet to the second or from first to the 11th cabinet, you will only have 3 hops between your node to your destination. Now, part of the solution also includes storage and file system. So we're basically getting an HPE Cray storage system that's called E1000. There's going to be 6 of these SSUs, which are scalable system units, and total usable file space will be about 60 petabyte. Now, if we wanted to expand this, we can expand it during the life of this system by adding more racks, and we can grow this. We had a requirement of minimum 300 gigabyte per second, and this will exceed that requirement. And this will come with a metadata that's on flash or SSDs. All of the file system will be on HDD, but the metadata will be on flash. And this is built upon Cray's Lustre file system. Now, this just gives you a little bit more insight into what's inside the ClusterStor E1000 system. As I mentioned, the parallel file system Lustre is based on the E1000 system. Now, this basically will provide our users with a global POSIX single name file space. Now, the E1000 can come in 3 different types of configuration. You can have all HDD, which is just a spinning disk, or all flash, which is just SSD, or you can have hybrid, a mix of SSD and flash. And in our case, all of the file system is HDD, but the metadata will be all on flash. Now, another important part of the solution is the software environment. Now, after Cray got acquired by HPE, both companies started working on the integration of their software stack. The integration hasn't completed yet, so we are hoping that we will be able to play an important role in HPE making decisions of what feature and function of the different software they keep in their final stack. Now, we have been working very closely with HPE to finalize our software environment, because we want to provide our users with an ecosystem that is optimized for our application and our workload. But we also want to make sure that we provide enhanced availability and usability. So, some things that are not listed here, the Cray programming environment will be what most of the developers and users will be using. It is a highly enhanced operating system environment, reduced OS jitter, and has a much smaller memory footprint. but also we will be using the Altair scheduler. So you'll see the same PBS that you are currently used to on Cheyenne. And Casper will also move to PBS. So we'll have a single scheduler across the board on all of our HPC resources. We also have PGI compiler, formerly PGI compiler. Now it's called the NVIDIA compiler environment. And we will have 50 seats of Intel Parallel Studio XE compiler suite, and also the Cray compiler environment. So I quickly wanted to mention about our cloud bursting capability. The RFP required that the software environment should be cloud capable. Basically, what we wanted to make sure that our Antarctic mesoscale prediction system, AMS, whenever our on-prem system is down, needs to burst out. But we also wanted to extend that just beyond AMS for urgent runs like hurricane forecasting, special campaign, or even general smaller job overflow or large memory job requirements, which we may not have on-prem. Also, if someone has a specialized requirement for some special hardware, it doesn't make sense to install that on-prem if cloud has that available and you're going to only use it sporadically or rarely. So this slide, I just wanted to share the slide because I've been getting a few questions. Now, this is how the PBS Cloud Toolkit will work. This will ensure that jobs will continue to get executed without interruption as long as we have network access to cloud, and obviously as long as the user has cloud credit and the money to pay for that cloud usage. Then you will be able to just burst out to cloud. So what happens is that job will get submitted to a designated cloud queue. Then the PBS will basically keep monitoring that cloud queue, and then it will estimate the demand for cloud nodes. So if you've submitted a job there and it requires an 8-node instance, it will basically burst out to the desired cloud provider. Obviously, there needs to be some configuration that has to be put in place and launch that instance for you. And then when you have completed your job, it will unburst, release that instance. Now we are deploying this also on Casper because we want to make sure that we test this out, because a lot of times the software provider has claims, but when we test it in a real workflow environment, sometimes things fall short. So we are already starting to deploy this in this month on Casper, so we are ready when NWSC 3 arrives. Now this is another slide that I put in there after getting a lot of questions, because users were asking how will data move around. So this is just to give you an idea. So user submits their job on their login node. Now what happens is that your data is on the on-premises, either Glade or campaign storage or your file system. Now there are different ways of moving data or keeping data on the cloud, but I'm showing you what I think would be the most used mechanism in our environment, unless we sign some contract with cloud providers to have persistent cloud storage or other means. And then the cloud instance that PBS will burst out will be local, but then it will move whatever input data you need to run your job to the cloud instance. And then your data will reside on that cloud instance. You will run your job, and then your output data will have to be egressed back to your on-prem resources. So this is kind of what the data flow will look like. With that, I'm going to hand over to my colleague, Bill Anderson, who will provide you details on the system deployment.
Thank you, Irfan. Yeah, hi, I'm Bill Anderson. I'm part of the team that's responsible for the system deployment of the new supercomputer. So the system team is responsible for the low-level software and hardware. That includes things like accounting, the batch scheduler, networking, all the way down to storage and testing. So a wide variety of components. So now I'll talk about a few of these items and give you some details to give you some more information about what the system will look like, but also to give you a better sense of the work the system team will be doing to help deploy this new resource for the community. Next slide, please. So one of those areas of focus is the software stack. So a great deal of system software needs to be configured and managed in order for the cluster to operate as a single system. Let's imagine that every employee at UCAR, approximately 1,000 people, had 3 highly advanced laptops, and we wanted to connect them all together with a high-speed network, as well as a parallel file system, and make it operate as a single system. That's really the challenge here, and this software is a key part of making that happen. So over here on the left, I have a simplified approximation of the software stack from the system perspective. At the bottom, kernel drivers, then low-level device software, for example, interacting with the network interface card, then the Linux operating system, cluster management software itself, the parallel file system software, and finally, site-specific scripts and software. And these site-specific scripts are scripts developed by engineers on the team, and they interact and interface with all the other layers of this stack. So getting this software stack configured correctly is a key part, is a key goal we have. And so it's a big focus of the team. Next slide, please. So Irfan mentioned the 60 petabyte Scratch file system. So that's also a big focus of the team. So that's 4 times larger than the file system, the Scratch file system that's currently on Cheyenne. It does run the Lustre parallel file system rather than GPFS, primarily for capacity and performance reasons. So files will be purged, but files will have a longer residency period because of the larger capacity. So both Lustre and GPFS present a POSIX interface to users. So for most users, the interface will be identical. The same Linux tools will work, the same system calls will work, open, read, and close, etc. There are some advanced features that are different, but by and large, the user interface will be identical. But while the user interface is identical, the underlying system engineering is very different. So the system team is spending a lot of time learning how to manage Lustre in a way that provides the reliability and performance that the community needs. Next slide, please. Irfan mentioned this as well, so I'll just share a little more detail. We plan to cross-mount file systems to Casper and the new supercomputer NWS3. So the Glade 2 file systems, which are the file systems currently mounted on Cheyenne, things like Work, Project, Home, and Scratch, we plan to mount those on Casper as well as the new Super. The Glade 3 Scratch, the Lustre file system, that we also plan to mount on Casper and NWSC3. And finally, campaign storage and collections, we also plan to mount on Casper and NWS3. Our hope is that these cross mounts will facilitate workflows and enable folks to get more work done. Next slide, please. So yes, PBS will be the batch scheduler for the new system, just as it is for Cheyenne. And there is a new feature called cloud bursting. I'll just give a slightly different perspective of what that means with this plot here. So time is on the x-axis, computational demand is on the y-axis, and this dark horizontal line at 1.0 corresponds to the maximum capacity of NWSC3. So you can see the demand varies over time, but those places in the curve where it goes above 1.0, that's where the demand exceeds the capacity. Those are areas, those are opportunities where we can burst to the cloud, take advantage of cloud resources to augment our on-premise resources. So this will be an area of focus for the team too, because there will be a fair amount of work integrating our on-premise resources with the cloud resources. Next slide, please. Finally, I want to give a shout out to the team. These are the folks whose hard work and expertise will be making all this happen. So thank you. And now I'll turn it over to my colleague, Michael Kercher.
Thanks, Bill. Again, my name is Michael Kercher. I am the co-technical lead for the NWC3 facility construction and physical integration portion of the project. Today I will be reviewing at a fairly high level the scope of our project, the status, and will also be discussing some of the engineering behind making the NWC a world-class supercomputing center, even as we reach the 10-year mark in our journey. First, I will be discussing the approach and scope we have developed to upgrade the NWC. Our facility and this project is centered on two main types of construction activities: capacity and fit-up. The capacity construction project allows the NWC to build up the back-end plant components needed to support a new HPC system, regardless of brand or type. The back-end components will last much longer than one HPC system, and in preparation for the additional loads associated with NWC3, it became quickly apparent that the NWC was in need of an additional 3 megawatts of electrical capacity. This needed amount is more capacity than the current computer room can support while Cheyenne is operating. So it was determined that the future computer room space at the NWC needed to be fitted out in a way that was more specific to these large bulk load systems that are typically water cooled. As we transition to the fit up of the NWC3 system, the scope of work becomes much more HPC focused, where we are installing a very specific number of circuits and the mechanical system is finished off to make final water connections to the cooling distribution units or CDUs. In order to complete this work, we have collected a very strong, talented team of internal CISL talent, as well as external partners who are familiar with our facility, mission, and who also understand that we are still a fully operating HPC center. I also wanted to give a quick shout out to Irfan for driving a new, more collaborative and creative project management approach where the respective technical leads are sharing information and trying to help each other mitigate risks whenever possible as the project progresses. Next slide, please. This slide gives some of the highlights of our current status of each of the construction projects. Our general contractor, Saunders Construction, submitted the building permit to Laramie County on the 4th of February. We have had some initial Q&A with the building department, but overall they seem to understand the scope of our projects, and they are excited to see the next generation of HPC get started up in Cheyenne, Wyoming. We are also working with the design team, RMH, and some of the key subcontractors to process submittals of proposed equipment that will be installed and also answer any specific questions about the project that may not be 100% clear. The processes are tracked through a very detailed system of requests for information, known as RFIs, and submittal reviews that also allow us to identify and order the long lead items that could impact the overall project schedule. The NWC3 fit-up construction package is currently being reviewed by UCAR Contracts and is being prepared for the NSF to review for approvals. The project team is also pursuing an effort to develop a letter of agreement with the chosen vendor, so an early start on the engineering effort for the fit-up can begin. Next slide, please. The NWC was designed with green computing features at the forefront, as well as capabilities for the present and future to take advantage of renewable energies available in the Cheyenne, Wyoming area. Currently, the NWC receives 10% of our energy from renewable resources. However, there is a strong effort by the local utility to expand these capabilities. And as a partner with the utility provider, the NWC will hopefully be able to capitalize on this renewable energy expansion in the future. Our green computing design features include things like 45-degree bends in our large diameter mechanical system piping to help reduce drag, allowing us to use smaller pumps to move the needed 2,500 gallons per minute of chilled water to cool these large systems. We also use a variable module management system associated with our UPS to reduce the amount of power used to protect our critical loads. Free cooling technologies have also been implemented with warmer chilled water loops, allowing us to use flat plate heat exchangers to cool our loads. Next slide, please. As I discussed in the previous slide, the NWC is very focused on efficiency and energy, especially in energy conservation, especially relating to the supercomputing and data center operations overall. We take advantage of the cool, dry climate in Cheyenne, and we also try to reuse as much of the heat created by these systems whenever possible. There's a strong focus on mitigating the biggest losses of energy. These include things like compressor-based cooling and UPS losses that I touched on earlier. but we also focus on energy loss through transformers in our electrical infrastructure. A great example of this is the NWC3 system coming to our facility. Approximately 90% of the load associated with NWC3 will operate at 480 volts, meaning that the facility only needs to use one transformer to step our utility provided 24,500 volts down to the needed 480 for the system. This makes the bulk loads as efficient as possible. You can also see the differences between our design and a more standard data center design in the pie charts on this slide. We have tried to reduce the operating costs as much as possible, and we always try to strive to be good stewards of taxpayer dollars at all times. I greatly appreciate the opportunity to be able to share this portion of the project with everyone, and I will now hand the presentation over to Brian to discuss the application readiness of the system.
Thanks, Michael. As Jeff mentioned at the start, my name is Brian Vanderwende, and I'm a member of the applications team. Next slide, Irfan. So there's just a roster of our team members. My co-lead is Rory Kelly, and what our team is really tasked with is to be kind of the outreach specialists with user groups and applications of interest for the machine. And I see this really as a two-way street. We're trying to collect information from those groups and about those applications that can inform the user environment as we structure it on the machine. But we also want to learn where we can help application groups and developers in terms of getting their applications ported and ready to go. Let's say they're interested, let's say you're interested in using GPU technology, but you're just kind of getting started with that. That would be a prime case where we want to learn what your requirements are, and also where we have information that we can help and provide training. So this diagram on the right here is just how I personally visualize kind of a flow of interaction with this machine. We're thinking about things like traditional interaction with a SSH terminal. We know Jupyter Hub interest and usage is growing rapidly. So that's something that we're trying to augment as well. And we completely envision, as Irfan said, the Casper system and the NWSC3 system being part of this ecosystem that's all served by the PBS scheduler and can burst out to cloud providers in a very natural and seamless way. Next slide, please. Irfan, next slide. I don't know if I'm just not seeing it. Okay. Looks like we need to go back a couple, actually. I think we missed two. Thank you. Okay, so just to talk a little bit about the software. We want to maintain a familiar user environment with the LMOD modules that people have told us are very convenient and easy to use on the login nodes, and we're trying to make sure that that environment looks as similar as possible across both machines. We're also trying to increase the usability and the capability of modern interfaces that people are excited about, like Jupyter Hub. We understand the collaborative workflows that enables, and we want to support that as best as possible. As Irfan mentioned, there'll be multiple compiler options with GPU and CPU support, of course. The Cray compiler, Intel, even though it's AMD chips, the Intel compilers have been quite performant on that in our tests. The NVIDIA compiler we expect will play a key role on GPU applications. And then we'll also have multiple NPI options. Cray NPI comes in the operating system software stack. We'll have Intel NPI. We see in VAPitch 2 being installed. And the key with these is that they're all MPitch based. And the MPitch NPI ecosystem right now is it's all ABI compatible, which basically means if you build an application using any of these, you can move them around in a portable MPI container to any other system that has one of those installed. So we see that as being very helpful for cloud bursting. Next slide, please. As I mentioned, we're also really focused on GPU computing. We have that 20% of the machine dedicated towards the GPU resource, and we're very cognizant of the growing opportunities in that space. A lot of this stuff we already support and have installed on Casper, so we encourage you to check that out and play around there if you haven't already. But in terms of coding development, we see things, we'll have the CUDA toolkit, of course, OpenACC for offloading operations onto the GPUs. OpenMP5 will also supports GPU directives, and we're installing compilers that support that on Casper now. We'll have things like the Magma optimized linear algebra libraries for GPUs and GPU direct MPI as well, which allows you to do direct GPU to GPU communications without having to deal with the CPU host. And then, of course, there's machine learning, deep learning, and artificial intelligence as well. So we'll support things like TensorFlow, Keras, PyTorch, Horovod, and more. Those are all Python libraries, but we're aware that there's also machine learning opportunities in languages like Julia and R and MATLAB, and we want to support those if and when users express an interest. So speaking along those lines, many are available in Casper now, and please let us know. Send in a ticket with user support, or email me directly if you have a software need or you want GPU consulting. Next slide, please. Just real quick, we talked about peer scheduling across and outside the complex using PBS. So we have the PBS Pro Job Scheduler across both systems. We really want this to look like a single system scheduling environment. So it's not as cumbersome to go across the machines. We really want this to feel natural. Built-in container support using Singularity. Singularity also supports Docker containers, and we can look at other container runtimes as well. Cloud integration, as Irfan and Bill mentioned, and also a graphical interface to PBS, as well as the traditional command line interface. And we suspect that will be most useful for cloud, but we're also looking at that for traditional jobs. Next slide. So just a quick timeline for early users. We're doing early porting and development work right now on Casper and some external machines soon. In fall of 21, we'll start accepting accelerated scientific discovery proposals. These are kind of big projects early in the machine to really do some big science that couldn't be done at other times. Targeted application work on the test machine, which will be installed around that time as well. And then in January of 22, early ASD users on the machine. And in April, open to all users. And sometime in the second half, we'll have Cheyenne, 22 will have Cheyenne be decommissioned. And as I mentioned, we're really focused on both our traditional codes and as well as these GPU codes that are growing in use and interest. Next slide. So just to wrap up, for my section, we're also looking at a very aggressive training timeline for users. So right now, or shortly, we'll be looking at doing workshops and programming using programming and using GPU resources. So really to get the user community more familiar with using GPUs. In the fall of 21, we'll do targeted early user training and application porting sessions. And then next year, we'll look at training for existing users on migrating, and also just general training on optimizing applications for both existing and new users and migrating job configurations to the new machine. So with that, I'll turn it back to Irfan to give a historical perspective and to wrap up.
Thank you, Brian. So I just wanted to share something interesting with you. In November of 1963, the NCAR got the first, the CDC 3600. Now the CDC 3600 was 3 megaflops. Now in November 2021, when we go into acceptance after 58 years, the new NCAR's HPC system will be close to 20 petaflops. So that's literally 9 zeros, and some change from what we had before. So getting back to more serious business, the new solution has about 2,488 CPU only compute nodes and another 82 GPU nodes. All of these nodes are AMD Milan. The SKU that we are getting hasn't been released yet, so I can't share that information on the request of the vendor. but in the next couple of months, AMD will be releasing that SKU. And there's about 692 terabyte of memory across NWSC3. Now, with such amount of nodes, you have to make ensure that the reliability, availability, and serviceability, usability, and manageability of the system is taken into consideration. And that's why what we call RASM, which is all of the things that I just mentioned, was of significant concern to us. So we are making sure that critical electrical and mechanical components, especially the file system and login nodes, will be on uninterruptible power supply or UPS. But we also have contractual obligations from the vendor to provide 99% availability on the file system and 98% on the compute nodes. But we are also looking at software and hardware features to see how we can integrate them into our environment for better usability and availability of our user workload. We are also working with the vendor to architect features that will use AI for higher RASM. So HP has something called AI Ops, which is artificial intelligence for operating operations center. And that's something we will be collaborating with them as well. So this kind of just shows you where we were and where we are right now. You can see the new system, while it is in parallel with Cheyenne, will be almost more than 25 petaflop. And then when we decommission Cheyenne in July of 2022, so just kind of gives you a historical perspective. This one basically is very interesting, and something that I care about is the power consumption. If you look at Cheyenne, it has 73 sustained megaflops per watt, but the sustained megaflop per watt for NWSC3 will be 171. That's almost 2.6, 2.7 times of Cheyenne. So we are mindful of the carbon and power requirements of the new system. This slide here gives you a historical perspective of our file system. As you can see, we will be above 100 petabyte of total file system space with the campaign storage, Glade, as well as the 60 petabyte scratch of the new system will be added together. So that's a significant amount of storage that has to be managed. Now, the data analysis and visualization and machine learning resource for NWSC3 will continue to be Casper. Now, recently we added more new hardware and more new processors to Casper. So a significant amount of GPU nodes were added, and we also added 64 high throughput computing nodes, mainly for embarrassingly parallel workflows, single node jobs, or even some shared type of workflows. These are all on HDR, as well as 100 gig Ethernet. There are 384 gigabyte RAM on each one of these nodes. We are also looking to add some large memory nodes to Casper. And in the next 2 to 3 years, we will refresh the technology on Casper while maintaining all of the scheduler, the file system that you are used to using on Casper. The idea for designing and architecting Casper is to make it more like an Acondo cluster, where we can bring in new hardware and new technology without having to forklift and throw everything out. So we will make use of the infrastructure, which is not just the racks and the power supplies, but also the networking. And so Casper will continue to be the data analysis and visualization resource. I also wanted to emphasize on campaign storage. Campaign storage will be mounted on NWSC3. And if you have a requirement where you do not want your data to be purged through the life of that campaign, whether it's 3 or 5 years, then you should talk to CISL for getting allocation. Here, currently it is 66 petabyte usable, but we do plan to add more space to it. This one is based on spectrum scale, not luster. And we have architected campaign storage in such a way that we can keep growing it without taking the file system down. And the good thing is it is connected to our HPC backbone Bifrost. So we can add more networking resources if the network gets congested or throttled. So another thing I wanted to share with you is what Brian mentioned before, that we are mindful that 20% of the sustained capability of the new system will be GPU. So we want to make sure that we not only provide the necessary training and any kind of engagement that the user community may want, but we also want to assure our user community that we will be taking the GPU software environment very seriously. It's not a staging environment. It is going to be treated like a production environment, because the software on GPU is maturing, but it does require regular maintenance and upgrade. And we want to make sure that users, when they move or port to GPU, they do not hit roadblocks because of user environment or software stack. And that's why we will be putting more emphasis on providing a more stable GPU software environment. And we also want to provide any training, not just within CISL and HPCD, but also to the user community. We can facilitate that engagement with NVIDIA, AMD. We can definitely facilitate that. So if you have any such requirement, reach out to consultants. And we also have Casper, where we have significant GPU resources. These are the latest Volta GPUs. Although we are getting the Ampere Redstone on NWSC 3, those are not yet on market, but you can use the Voltas on Casper to get ready for GPU. And here's my final slide. I just wanted to kind of, again, it was mentioned about the naming contest. We do not have a name picked for NWSC3, and that's why I keep using the term NWSC3 instead of the name. We did have a contest which ended in January. Students have already submitted close to 200 different proposals for names. And we did provide some guidelines on what would be good names for HPC systems. Now, the CISL Council is going to evaluate those submissions, and then in spring, we will, after consultation with NCAR and UCAR Legal, as well as NSF, we'll make that announcement. And then the winning submission will get a prize along with the students of that class, the rest of the class as well. So here's a timeline of the deliverables, what you can expect. So we are currently planning on the implementation and commissioning. So we are kind of working with HPE and the other subcontractors, but then we will do a factory trial in August, and then the system will get delivered on before or on 1st of October. And then we will start working on the installation in November, and then start the acceptance testing in late November and completed by third week of December. And then January 3rd, our plan is to open the system for accelerated science discovery. And then in April, open it up to the rest of the users. And with that, I just wanted to shout out to all of the teammates who have contributed to this, especially some of the slides were from HPE and Altair, but Bill, Brian, Michael Kercher, Gary New, Tom Engel, Mark Genti, and a lot of other folks in HPCD. With that, I'll open it up to questions. So if you have any questions, we will be very happy to answer that. But if you cannot get your questions to us during the rest of the time, feel free to email any one of us, and we'll be more than happy to get back to you.
Great. Well, thank you very much, Irfan, Bill, Brian, and Michael. I think we do have a few questions. Yes, here I'm seeing them in the Slido. So I'm going to read them, and I'm not sure, Irfan, if you or one of your colleagues is best to answer. So I'll let you guys decide. But the questions are in order of who upvoted them. If you do have any last minute questions, please type them in right now or upvote ones that are there, and you may influence what gets read out. First question, will users have to pay for the cloud bursting, or is that part of the package?
So currently we are working on that question, because obviously there needs to be some funding to pay for cloud usage. We do have money allocated and reserved for AMPS, but for the rest of the users, CISL is working with UCAR and NCAR and other labs to come up with a system through which we could allow users to burst out and they will have cloud credits. I don't have an answer because that is still underway, and unless that is reaches its conclusion or is run to the ground, we won't know for sure.
Great, thank you. Next,
if you want, I can see the questions and answer them to save time if you're fine.
sure, that's fine. We can try that, but do read them out before answering them, just in case others.
Yeah, so the next question is, how does the cloud instance bursting get provision? Is it going to be containers in AWS or Azure? So right now, the idea is that we will be able to use whatever container that AWS or Azure or other cloud providers provide, because the PBS toolkit works with all the different types of orchestration that AWS or Azure or some other cloud providers provide. We will be doing some testing on Casper, and we may actually limit the number or types of container we allow, because it's difficult to support all types of container, but we definitely are looking at Docker and Singularity. Brian, do you have anything you would like to add to that?
No, that sounds good to me, Irfan.
So next is from Linda Mearns. If 10% of the energy of electricity from computing center comes from renewable, what is the energy source of the remaining 90%? Michael, do you want to take that?
Yeah, I can. I'm not quite sure what percentages of the remaining 90% fit with what fuel source, but I do know that Black Hills Power has some natural gas turbine generators in our area, and then there's also some coal-fired power plants in the northern part of Wyoming that make up the rest of the power, if that helps answer the question.
Thank you, Michael. So the next question is, will Notebook hosted on the Jupyter Hub be runnable by people who do not have UCAR or NWSC3 account? So I'm just going to make an assumption. You're talking about the Jupyter Hub that we currently provide as an environment with ISD and TDD. So Brian, do you want to take that? I'll just kind of take we don't have any plans to allow people who don't have account on our system to be able to use our resources. Brian, do you want to add to that?
Sure. Yeah, I'll just say that, in terms of any notebooks that were hosted in some sort of interface, that's going to be behind the wall, as Irfan mentioned. But, the whole principle of a notebook is that if you have the software stack installed somewhere else, that notebook is totally portable to any other system. So, that's kind of an in-between answer, but I think we'll be looking to facilitate sharing wherever possible.
So the next question is, will Intel and GNU compilers will be also on the system? Yes, there will be 50 Intel compiler suite available on this one, and definitely GNU is open source, but I will let Brian add to that. Do you want to share your plans for GNU environment?
Yeah, we'll support GCC, and I guess I can address the question that just popped up as well. We're going to look at Clang. So the question was, has the support team considered adding Clang compilers to the software stack? Yeah, we're looking at that. Clang has some interesting offloading capabilities as well. Now, the NVIDIA compiler is also LLVM based, so we want to make sure that we're not fragmenting things too much, but we're going to look at any compilers that make sense.
So Brian, you did the second one, then the debuggers. What debugger will be put on the system?
Yeah, sure, I can take that too. So we'll have the ARM Forge utilities that are on Cheyenne and Casper. We'll have GDB and gprof and sprof and those standard utilities, and we'll also have the Cray performance analysis tools suite, which comes as part of the Cray programming environment.
Like there's one last question, Irfan, from Summer. Is the Dragonfly topology 1D, 2D, DF+, or other?
Yeah, Bill, do you have any insight to that?
Yes. I think it's considered a variant of 2D, essentially, a 2D variant. You have all the nodes, each node is in a cabinet, each node is connected one of 16 switches in that cabinet, and then those switches are in turn connected to switches in other cabinets. So I believe it's considered a 2D variant.
Great. Well, that's the last of the questions that were submitted. So Irfan, Bill, Michael, and Brian, I want to thank you for giving a extremely informative seminar. Looks like your email addresses had briefly popped up on the screen. I'm sure we'll be able to figure out how to reach you if we have more questions, but definitely sounds like a very impressive system, and we're looking forward to having it on the floor. So thank you very much.
Thank you, everyone.